to our KOBOLD Instruments webinar hosted by Peerless. My name is Greg Barrell, and I'm excited to introduce this session where we'll explore KOBOLD's magnetic flow meters and ultrasonics from a product-first perspective, focusing on their role in today's evolving energy and process industries. Joining us today is Cliff Spiegel, application engineer, and Scott Cunningham, sales manager at KOBOLD Instruments, who will share their expertise regarding the next generation of flow measurement technologies. Before we dive in, I'd like to introduce Peerless. We've been a trusted advisor, a trusted provider of process components over 111 years, working with customers to solve complex challenges across a variety of industries. We take pride in delivering solutions that prioritize safety, efficiency, and reliability. There are three facets to Peerless. We have our Peerless Process Division. We specialize in supporting manufacturing customers in the chemical, food and beverage, pharmaceutical, power, and other various industries. We then have our Procore division, which supports our OEM customers, custom equipment engineers, skid builders, EPC firms, and large capital expenditure projects. No matter the challenge, we strive to provide tailored solutions that meet our customers' needs. And then we have our high temp fabrication division, which machines scientific surfaces for laboratory and medical applications and provide electrical insulators and refractory solutions. By leveraging non-metallic materials and our years of experience, we ensure high quality results for even the most demanding applications. We have a vast network of manufacturing partners that support Peerless and our large customer base. We've aligned ourselves with these important partners to ensure our customers get the best products and services for their key applications in their facilities and custom equipment they are building. So with that, now I'll hand it over to Cliff and Scott, who will take you through the details of these innovative solutions and how they can address your specific needs. Let's get started, guys.
All right. Just make sure everybody can see my screen.
Perfect. And then Scott, before you start, I actually just have something to mention on questions. So we want to make this presentation as beneficial as possible for everyone. So we encourage questions throughout, and there's a couple different ways you could ask those questions. The first is by clicking on the chat icon in the toolbar up top. The chat window should appear if it's not already there, and you can just drop your question in there. When an opportunity arises, I will ask Scott and Cliff. You may also raise your hand throughout the presentation. Currently, everybody's muted, but I will see that you have a question by hitting that raise your hand button, and I will unmute you again when an opportunity presents itself, and then you could ask your question directly to Scott and Cliff. But that's really it. So Scott and Cliff, take it away.
All right. Well, thank you very much, Charlie, and thank you, Greg. Just want to first say thank you to the Peerless team. We really appreciate the opportunity to be part of this webinar series. And when Peerless came to us and asked if we want to be part of it, first answer was absolutely yes. Then the follow-on question was, well, what do we want to talk about? So I've got Cliff here with me. Cliff's one of our longtime experts here at KOBOLD. And the topic that seemed most apt was some of the newer flow technologies we get asked lots of questions about. And there's a lot of buzz about magnetic inductive and ultrasonic flow meters. So hopefully throughout this presentation, we'll kind of demystify those things for you and give you some good insights that you can use when doing your own process selection. Let's get started. All right. So like I said, what we'll cover today, we're going to talk about ultrasonic flow meters, magnetic inductive flow meters. We'll talk about the advantages of each technology. We'll go through some specific examples of where these technologies have been applied. We will also touch on some things you need to consider if you're looking at potentially incorporating these technologies into your processes. And then lastly, we'll finish up with a summary slide, quick side-by-side comparison, when to use one technology versus the other, maybe, or where there's some kind of overlap. And then lastly, as Charlie mentioned, we want to make sure we address some of your questions, and I've got Cliff on here to help me with that portion of it. All right, so let's just jump right into it. Ultrasonic flow meters. When we talk about ultrasonic flow meters, this technology is essentially full bore, meaning that there's no moving parts in the flow path. There's nothing to wear out or break down. Obviously, that leads to no degradation, no maintenance costs associated with having to sort of replace paddle wheels or replace flow meters because of wear and tear on the mechanics. We get extremely long service life, and because you don't have anything in the path, you don't have any pressure drop, which means you've got reduced piping costs, and you don't have to compensate for pressure drop with over pumping your motor, right, Cliff? That's
yeah.
These ultrasonic flow meters are very versatile. We first launched, we could only do water or compensate for water. Now we've got a lot of different media configurations. We can do all sorts of fluids, oils, fuels, glycol, with a whole range I'll get to in a bit. And then the size of these makes them, easy for installation in tight areas. They're extremely high accuracy, and they have what's referred to as a really high turn down ratio of 250 to 1. That means in terms of range, if with traditional flow meters, maybe 10 to 1 is what you might get from a variable area or paddle wheel. And when you're talking 250 to 1, that means you can go from 1 GPM all the way up to 250 GPM, and that's a huge range in which you can measure. Anything else to add on that slide, Cliff?
No, it's pretty basic.
So I've actually holding one of our inline ultrasonic flow meters, and I'll get to this in a second. But when we look at where this type of technology is applied, there are lots of potential uses for both inline and clamp-on ultrasonic. So I'm going to use my mouse. Hopefully you guys can see this. The ultrasonic inlines, we have OEM, medical imaging OEM customers using it for coolant lines. Data centers, it's important that they be able to measure and regulate flow across for cooling circuits, battery cooling, anything in the air conditioning HVAC space. We get some applications for chemical dosing, lubricants, measuring the flow of lubricants. And then when you get into anything with deionized or demineralized water, as we'll touch on a bit, this is a technology that doesn't require electrical conductivity of the media. And then also when you get into fuel consumption, the ultrasonic is useful there as well. And I've got some different photos here. This is a photo where you see a number of different flow meters being used for distributed wastewater lines. And then on the right-hand side, you're looking at the clamp-on ultrasonic technology. You've got a processor here, the user interface for our portable setup, and then your transducers. There's different sizes. Those can be placed on the pipe, and the software kind of walks you through based on your diameter and wall thickness and material type. It'll tell you how far apart to put the transducers, how to do your setup, and then you can start measuring flow without breaking into a pipe. So again, some of the advantages that we'll touch on here as we get into it more.
Yeah, and Scott, for something like the clamp-on meters, especially the portable, you may want to just measure flow temporarily. It's not a permanent installation, so you can check out things in someone's plant or whatever. They can move it to different places. So this is not necessarily for the portable model. It's not necessarily a permanent installation.
Yeah, good point, Cliff.
And some people like to use them to verify the functionality of meters that are currently being used in processes. It's kind of like a check, or not. I don't really want to say calibration, but it's just verification if their current flow meters are working correctly.
Yeah. Okay.
Hey,
Nice.
Scott and Cliff, we do have a question in here.
Sure.
It says, does vibration cause distortion in flow measurement?
Yeah, possibly. Yeah, I don't know if we could answer that. Pretty much all equipment vibrates to some degree. But really what you're measuring is the speed of sound going through the media. I don't know if that's directly going to affect the reading or not. But
Yeah.
anything is being pumped, there's vibration taking place.
Yeah, so the devil's in the details there, but yeah, that's certainly a consideration we want to take into account, right, Cliff?
Yeah, I don't think I've ever heard a concern about that, if that means anything.
Yeah. Okay.
Perfect. Thanks, guys, and feel free to ask a follow-up if you do have one. And then we do have another question as well, and I'm not sure if you're going to touch on this at any point, but any hazardous area classification for these that you guys have?
For ultrasonic, yeah, we'll tackle that one a little bit later when we get into the Q&A, and because it depends on the product and what rating we're going to be able to apply. So,
well, I actually flowing in. I actually got one more. It says for glycol water mixtures, would buildup of ice on the piping affect ultrasonic readings?
It depends which meter. If it's the clamp on, as long as it's not between the transducer and the pipe, it shouldn't matter. And when those are installed, there's actually a coupling gel that you put on there. So I don't really think moisture would be able to get underneath the gel. There is another point to that. If you got a 100-year-old pipe that's got 3 inches of paint and 2 inches of rust inside, it's not a good place to mount the meter.
Yeah.
So pipe conditions matter. But if it's put on when it's dry and clean, I don't believe ice buildup should matter. But you just can't get outside of the parameters, whatever the temperature parameters are for the sensors. And there are temperature limits.
Okay. Yeah.
Thank you, guys.
Thanks, Charlie. Okay, so there's a media table. The reason I'm showing you this is just so you can understand the wide variety of media we already have set up to run through our ultrasonic flow meter. And there's more. This is just an excerpt of some of the media that we have. And then I know the font's kind of small, so I pulled some of them out, some of the more common ones that we see. Top of the list, glycol water mixtures. So we have 100% water, we have 20% water glycol, 34%, 39%, 52%, just a lot of different percentages, because that'll all come into play as I'll get to in a second when I talk about how the technology works. Solvents, ethanol, seawater, like I said, fuels, oils, and lots more that can be used with this technology. So some considerations, things to consider when you're doing using ultrasonic flow meters. Straight pipe run requirements. Ideally, we would have a 10x and upstream and 10x downstream straight pipe run. That's going to give you the highest accuracy. We've certainly implemented in cases where we don't have that, but again, if accuracy is your goal, that's best practice. Like I said, the media viscosity we can account for, and if you're using a temperature compensation, that's even better for increasing the accuracy of the instrument. Again, because there's no real obstruction in the path, you've got low pressure drop, and then like we said, we've got extremely high rangeability, meaning from the min and max, and being able to measure pretty much the full operating range. As Cliff mentioned, you like with all of our flow meters, you do need to have full pipe. And then Cliff also mentioned this too, the clamp-on technology. You're going to make some assumptions of that pipe condition, right? So if you're going to give it a wall thickness and a material type, and you don't realize that there's scale built up on the inside of the pipe, your accuracy is probably going to be affected, right? So some of those assumptions and considerations you just need to keep in mind as you look to implement the technology. Anything else on that, Cliff, before I jump into how it works?
Yeah, this kind of says something about it, but we were talking earlier. Pretty much with what either one of these technologies, ultrasonic or mag meters, what you're doing is you're actually getting the velocity of the liquid going through the meter. And when you get the velocity, you have a known cross-sectional area, and that's how it calculates flow rate. So really what you're doing is you're measuring the flow velocity.
Yeah, good point. Well, that's a nice tie-in with how it works. I did wanted to show you the DUK inline ultrasonic flow meter that we offer, and show you a little bit about how it's operating. So your media in this case would be flowing in this direction. You have a signal, ultrasonic signal being transmitted from this side, and a receiver on this side. You also have one down here that's sending and receiving. Since your media is flowing in this direction, just like if you were going to say paddle from one dock to the other dock across the river, if there's no flow, the time it takes to get from here to here is the same as it gets from there to from the other the other side. However, when you introduce flow, the faster the flow, the more impact it has on the time it takes to get from this one to this side versus this sensor to that to the downstream sensor, right? So now you have a time differential, and that time differential we use, it's directly proportional to the flow rate or the velocity, and then like Cliff said, then we're calculating the flow rate based on the velocity of the fluid. So that, in a nutshell, is how it works. Any questions on that? All right. Well, that wraps up ultrasonic technology. Now we're going to get into talking about magnetic inductive. So you'll see a lot of overlap here, and like I said, when we get to the end, we'll kind of use, but magnetic inductive, you don't have any moving parts. You don't have anything in the way of mechanical wheels or gears or things that can degrade over time. We don't have any maintenance costs associated with it. There's no upkeep, and you don't have any obstructions or restrictions that would cause pressure drop. Magnetic inductive flow meters can be used with a wide range of media. You can use it with clean water, sanitary applications, but it can also be used in applications with wastewater, dirty water, corrosive media, or even abrasive media. So because of its compact nature, it can be installed in some tight spaces, extremely high accuracy, and depending on the technology, it has a really high turn down ratio compared to traditional, variable area or paddle wheel technology. And it's either, 40-1, or even in some cases, like our small MIM, we have ranges that are 250-1. So again, really high turn down ratio from the minimum to the maximum, where we can give you an accurate measurement. And up here, you'll see a few different types of technologies. Well, sorry, they're all the same technology, but they're applied in different ways. So this is an insertion example. This is a flanged inline example. This is, we'll talk about in a bit, our plastic housing for special media. This is another inline solution, and then another flanged offering. So a wide array of technologies, or of products that use the same technology. So getting into where these are used, how these are used, you see a lot of different examples here. This top example basically shows a mag meter like the one I'm holding in my hand, but without the display electronics. So this is a mag meter. We've had cases where they've put these in, say, like an environmental chamber, and then you isolate the electronics external, and you can read what's going on inside that flow meter. So that's a remote mount option. You see we've got flanged options, and then when you get over into different chemicals, maybe chemicals that aren't as compatible with stainless or other metals, then we do have some plastic housing solutions for those more caustic media.
And so, Scott, on the remote, on the MIMs with the remote displays, there's a couple reasons why you might want to use that. One of them is if the pipe is in an inaccessible area that you can't read the meter, you're moving the display to where you can, and I believe you can get up to like 15-meter cable, very long cable, or you can actually increase the temperature range of the meter beyond what it would be when the electronics are built in. Just two basic reasons why you would use the remote, and that's also available on the large EPS meters also. Same thing.
They're the large flange ones. Yeah. Thank you, Cliff. So again, this technology, a wide range of applications. Over on these photos here, you can see some different applications. This down here in the bottom is an insertion style, so it can be used on really large pipes, ones where it may be cost prohibitive to try to do an inline flow meter. Again, all of those things that are taken into consideration, we're looking at what's the right solution for your needs. But some of the more common ones: water, wastewater, slurries, pastes. With the plastic body one, this is an MIK. Like I said, we can do acids that wouldn't be compatible with metal. We also have examples using running alkalis through, or even corrosive liquids. Anything I'm missing on that, Cliff?
No, they're very common in waste treatment, where they're used for metering chemicals into some other process. Yeah, if you have aggressive media, the MIK is what you're looking for.
Yeah, yeah.
There's various material combinations and electrode choices too.
Oh, good point. Yeah. So we'll get into that in a second. We'll talk about how it works. Similarly, with ultrasonic, we do have some upstream and downstream straight pipe run requirements for best practice. I think it's what is it, Cliff? 3x upstream and 2x downstream for the MIM.
Yeah, let me take.
So a little less than ultrasonic, but again, those are some best practices for us.
MIM is 3 and 2.
Okay.
And these are relatively small meters, so it the worst case, I mean, there's a 2-inch one, so it's 6 and 4 inches, so it's not much in this type of meter. It's not for an MIM. There was a couple questions that popped up. Did we want to
Yes.
look at them?
Yes.
I saw it briefly and I knew the answer, but now I forgot what the question was. So,
Yeah. So the first is specifically on the
C3.
MIK series, whether you could have the C3 T0 display remote also.
No, I have not seen that. I don't know if Scott, have you seen that? It's on the MIM.
Yeah, I haven't.
The MIK, that is not an option that I've seen at this point.
Yeah, we'd have to look into that. There are some other electronic options, and we may be able to run that to like a secondary display. We do that quite a bit, but that's a very specific. This is the C3T output, so that's a very specific question. We can look at that in more detail. But like if it were running to a secondary display, I think we could probably do that, maybe a blind output or something. But yeah, we'll see.
And I think there was another. I don't know if we touched on it as far as conductivity.
I have it.
Limits.
It's right here. Yep.
Yeah, there was another comment. It says the magnetic will not work on pure demineralized, deionized water unless something revolutionary has changed in the technology. I don't know if you guys can comment on that at all.
That's right. So yeah, I was going to get into that when we talk about the considerations and how it's actually working. But yes, the media has to be conductive in order for a magnetic inductive flow meter to work, and I'll get into that here in just a second. So let me kind of work down through some of the considerations. So
there is actually one more. Sorry, Scott. Before you, I guess, move on. It's do ultrasonics require a certain amount of bubbles or particles in the media to work?
No, in fact, it's better if they don't have bubbles in there, because that will affect the transmission speed.
Okay, perfect. Thanks.
So back to the magnetic inductive, some of the considerations. So it really is not a suitable one for hydrocarbons or for gases. The media cannot have magnetic materials in the flow. It does have, as we said, really good rangeability, low pressure drop, and minimal obstruction. And again, like all of our flow meters, it does require full pipe for operation. Now, getting into the conductive, electrical conductivity requirements, it depends on our meter product, right? So we have some product families that require greater than 5 microsiemens per centimeter, and we have others that require greater than 20 microsiemens per centimeter, but they all have to be, there has to be a minimum electrical conductivity in the media. So that makes it not suitable for, fats, demineralized or deionized water, even oils, right? Anything that's not going to be thermally or electrically conductive. So the reason behind that is actually how it's operating. So similar to a motor and a generator, when the media moves through there's a magnetic field, and when that conductive media moves through that magnetic field, a current is induced, and that current that's generated is directly proportional to the flow rate, or the velocity, really, as Clifford mentioned before. So as you increase the velocity flowing through the pipe, your current is going to increase proportionally. And then we use that velocity with the area to figure out what the volume over time is, right? So the flow rate. Anything to add on that, Cliff?
No, other than the you have to know your conductivity. And there is a range, and it depends, some of them, on the electronics. Like the highest requirement is on some of the MIKs, which MIKs in the three smallest ranges, it actually goes up to 200 microsiemens. But most of the other product is much lower than that. It's 30 or less, and some of the products it's 5.
Yeah, and again, that's not something that's going to influence your measurement. It just needs to be above a threshold for it to work, right? So if you have a media with a higher conductivity, it's not going to give you a different reading. It has to be above a certain threshold, or you're not going to get any reading, if that makes sense. Okay. So at this point, we've covered high level ultrasonic, and we've covered mag meters, and we've put together this kind of comparing and contrast, right? What are the advantages? Why would you use one over the other? And we get asked this all the time. So really, when you look at ultrasonics, if it's a non-conductive media, but you're looking for all the advantages of, no moving parts and these newer technologies that are repeatable over time, it's a great choice. You also have the added benefit of being able to use clamp-on ultrasonic, so you don't have to break into a pipe. You don't have to do any plumbing or line break-ins. And when you get into really large pipe diameters, sometimes a clamp-on technology is more cost-effective than trying to find an inline solution using maybe mag technology. You have extremely high turndown ratios, like we said, 250 to 1. So some of the downside to ultrasonic, it's still not used as much as magnetic inductive technology. It's not quite as popular, and it's a little bit more expensive for the inline solutions, or even the clamp-on, versus some of the magnetic inductive equivalents by line size. On the other hand, magnetic inductive, you get better accuracy for lower flow velocities. It's a technology that's been around for a while, and it's well trusted. And then we do also offer, with magnetic inductive, we offer insertion models. And the insertion models, these can go into large lines and don't require, a large flow meter. I've got in my hand here I think one of our 3-inch MISs, but you can imagine if we had a 24-inch line, these things can be really quite large and quite expensive. So, Cliff, you said there's a crossover point,
Yeah.
Where you go from insertion to flange, or vice versa.
Yeah, somewhere 10 inches or so above that, it may be more cost effective to use an insertion. But I believe we go up to, in the regular flange models, it might be 14. No, actually, we make those up to 24-inch diameter.
Yeah.
So they're pretty big, and they actually can make them bigger, but yeah, it gets very expensive when you get into the bigger sizes. There may be other ways to do it. We sell them, but it's not always going to be the first choice.
Yeah, that's it. And some of that stuff might be where, like, we have the con here that says no clamp-on models, right? So when you get into those really large pipe sizes, you may want to pivot back to clamp-on ultrasonic, or, like we said, insertion style. So anything else before we kind of move on to the Q&A?
Yeah, I don't know if you might have just addressed that with the clamp-on pipe ultrasonics having issues with the higher pipe skin temperatures.
Let me look at. I'm looking on the DUC data sheet, and 300F is pretty much the limit for the clamp-on ultrasonics. The flow-through ones, I I believe, are less because the electronics are attached. Yeah, they're 194. So yeah, there are limits for either one.
Perfect.
As far as regular mag meters, depending on the liner material, it could be anywhere from it has roughly the same high. It has the same high limit, 300. Depends on the liner material. It goes down to 158 for soft rubber and up to 300 degrees for PTFE or EPDM.
Thanks, Cliff.
Perfect. And then as we open it up for questions, we did get one right away. It says, what information / properties are required for a fluid other than water to compensate in ultrasonics?
Oh, both of these, the clamp-on ones, there is a database built into the DUC. I don't know if we have that list separately, but
I do, yeah.
you want
for the DUC, I don't, yeah.
the DUC, yeah, the DUC, you actually select the media when you're setting it up, and sometimes if there's something specific, if we don't know, we could ask the factory if they have any experience with it. On the DUKs, there is a listing on the data sheet of just various, whatever, glycol, oils, some other chemicals. There's some fuels on there. If it's not on there, we could ask.
Yeah, we've had them customized before as well. So it's just a media file that has that compensation in it. So yeah, we just really need to know what that media is, and we can figure it out from there.
And pretty much the media configuration, it's based on the transmission speed through that media. How they measure that, I don't know, but that's and whether it's done by testing or it's just a physical property, and they could put that velocity in the calculation to compensate. Like Scott said earlier, when these first came out, we could only do water-like materials, but when we went to the C3T electronic output, that's when we can add in these additional compensations for different media. But if there's something specific that we don't know, we would just have to ask.
Perfect. We did get a thumbs up, so great job answering that one. Okay, got another one. I think you mentioned this a few times, but can you further explain and dissect what turn down ratio is when it comes to flow meters?
Yeah, do we have, I don't know, Scott, if you could bring it up handy or just, let me see where I'm looking on the DUK. It's on a lot of them. On the DUK data sheet, on page 3, it shows the different ranges. I don't know. Are you set up to share?
Yeah, I guess really just to kind of explain what that means a little bit more, Cliff. That's really, I think what they're looking for is when you talk about the range, it's from like 1 gallon per minute to 250 gallons per minute, or some ratio like that, right? 10 to 2500. And so you're really just getting that full range where you can get accurate measurements throughout the range. We have other technology, like you mentioned, variable area, paddle wheels, things like that. And then you have to really be conscious of where you want to measure within your given range, right? So you try to get the operating range kind of in the middle of your measuring range, or your measuring range in the middle of your operating range. But there's some trade-offs there, right? So you may not be able to see the very low end or the very high end, but you're kind of picking where you want to measure. I guess, would that be a good application of why that measuring range would matter?
Yeah, let me see if my share works here. Okay, so this is right off the data sheet. Did that come through?
No. Yep.
Okay. So for example, if we pick the second one down here, so on the high end it's 10 GPM. So it's real simple. You take 10 and you divide it by 0.04 and you get 250. So on this particular meter, it can measure from 0.04 GPM to 10 GPM, which is a factor of 250, and that'll carry down the line. Some of these may vary a little bit from rounding, but that's tremendous. Not all flow meters can do that.
Yeah.
But these type of whoops. I almost ended this. I almost ended the presentation. But did that turn the share off?
Yes, yeah. Well,
Okay.
you're all set there, and then just
So,
maybe one
does that
more.
make sense? It's pretty much just it's the ratio of the highest to lowest measurement that a given meter can make.
Perfect. Thank you.
And things like variable area and some paddle wheel and stuff. And that's just not us. That's just a physical constraint. But a lot of the traditional type flow meters are nowhere near this.
Yeah.
Perfect. Thanks, Cliff. And then, given the requirement for a full pipe in both technologies, what are some practical challenges you've encountered in the field during installation, and how have you addressed them?
As far as full pipe, and again, that's not KOBOLD. That's anybody. If you want an accurate reading, you need a full pipe. There can be cases with mag meters, if you don't have enough liquid in the pipe to touch the electrodes, it's not going to work at all. And our meters will actually give you a warning that they'll say empty pipe or whatever. They'll give you a warning that it's not, that you have no conductivity. But if you're designing a system from scratch, pretty much any type of flow meter, any technology, the best flow direction is bottom to top, because you will always maintain a full pipe. If you're running other flow directions, it's possible that your pipe is just going to, if it's draining into a tank, your pipe is just going to empty out. If there's nothing holding it back, you can have the pipe kick up at the end to keep it flooded. There's some examples in I believe in the EPS data sheet, or maybe in the manual. Yeah, so it's just piping considerations, the way the meter is oriented. But that's just good engineering practice, the way they're installed. It's better to have a pipe going uphill than downhill, and that's how you should choose your meter location, not by what's convenient.
Good point, Cliff.
Thank you. I'll give it another. Sorry, go ahead.
I can. Let me throw this on the share real quick. This is actually in the EPS data sheet. So this shows something where, like I said, you kick the pipe up at the end to keep it. You can't always do that, especially if you have solids. It can build up. It is something you don't want. You just don't want it dumping out. in this case here, you would always pick the uphill run as opposed to the horizontal or downhill. And there's other type things, but that's, yeah, here's some mention of vibration. That has to do with how the pipe is supported. Anyway, I'll take that off, but that should be enough on that.
Yeah,
Perfect.
thanks, Glenn.
Yeah, thank you. I'll give it another couple seconds to see if there's any late questions before we close here.
And there were some questions asked earlier, if we wanted to touch on them, if we have time, or if we haven't done them already.
Yeah, I think the only one that we might maybe breezed over a little bit was the hazardous area classification one.
Oh.
I don't know if there was if that applied to specific mag meter or dependent on.
Yeah, so
let's leave it at that.
Some of our meters have ATEX approvals on them. Not all of them. Now, what I will say about explosion proof, it's not up to us, and it's not necessarily up to you what's required. The end user is responsible for telling you what's acceptable in their facility. So it could have to do with their insurance, but I would be very careful recommending a specific explosion proof rating to a customer. You could tell them what's available, but ultimately it's up to them to tell you what's required. So on some of our products, it will generally tell you in the, trying to find one. I thought it was in one of these had it. Yeah, like for example, the PIT right on the front page of our data sheet, if it says ATEX EX, there are hazardous area approvals available for this, but not everything has it. I think of the stuff we've discussed, just the PIT and the DUC have it. I don't know if anything else does.
Yeah, I think the
Yeah.
the takeaway is really there are a lot of details that are in any project that we're working on with customers, and so being able to schedule engineering consultations, working with the Peerless team and pulling in folks from our side like Cliff, we're going to help to kind of down select to what the right solution is for the application, considering all the variables, right? So and we try to understand the constraints and make the best selection really based on taking as much information as we can really learn about how this is, what the application requirements are and what the objective of the flow meter is really supposed to be doing.
Perfect. Thank you. And then I think that was the last question here. And I know we ran a little bit long, but I think that's because there were a lot of good questions. So hopefully everyone felt that this was impactful. So I just want to thank Scott and Cliff again, and Greg for being a part of this, and thank everyone that was able to attend on behalf of KOBOLD and Peerless. So we'll see you next time. Thank you again.
Yeah. Thank you, everyone.
Thanks.